Hello, everybody, and welcome to our first video in our course, Deep Learning. This course came actually after our course, Machine Learning, which I highly recommend you to take because it has all the basics for this course. And if you didn't take it, I highly recommend you to take it. If you already know about machine learning from somewhere else, it's highly recommended. If you don't know, it's gonna be a little bit hard for you. So I'm not sure is it going to be fine or not, but I really recommend that you take the first course about machine learning and then start out with this course. So what are we going to see in this video is we're going to talk about traditional learning and the existing problem that we're going to need to solve using deep learning or neural network for that matter. And also we're going to see a computer vision example. So what we had in machine learning is well, if you took the course, you know what are we talking about. If you didn't, I'm gonna try to make it easy for you. So in traditional machine learning, we learned about weights and biases, and well, we call them parameters, but now I'm gonna take it directly and call them weights, especially for deep learning. And so what we had is trying to learn what we called a hypothesis function. And the hypothesis function going to give us a decision boundary, which is this green curvy line, to separate the positive and the negative, to separate two classes. For example, we had in the previous course, we had the example of whether a tumor is benign or malignant. And we had X1, for example, is the age and the size of the tumor. So depending on the size of the tumor and the age of the patient, we can decide whether the tumor is malignant or benign. So yeah, and we learned about the sigmoid function and how it can help us to decide because it's bounded between 0 and 1 exactly. So if it's like less than 0.5, then it's not malignant. If it's more, then it's malignant, and so on. So, and the most important thing is about the decision boundary. We said that the harder decision boundary it is, like this is not linear decision boundary, so it's hard like to be curvy like that. The solution is when in the hypothesis function we just add some like multiply the features and make it like quadratic. We learned about the quadratic function and the cubic function, and so make it like quadratic and cubic and just multiply the features. It's like making new features out of the old features and make them quadratic. Like easily speaking, just make the hypothesis function more complex. In that way, you can get more complex decision boundary. So, but the problem is, here we have only two features. We have x1, x2. We don't have like 100 features. But imagine if we have more than two features, like let's say 100 or 200, 300, which is the case for in practical machine learning, and that's our goal, to actually practice machine learning and not just see examples. So if we have this kind of number of features, calculating the hypothesis function is going to be like almost like super hard or even impossible for our computers, no matter how powerful is your computer. So we need to come up with a new solution better than these solutions in the traditional machine learning. So let's see an example that show us more this problem. Let's see, we want to learn about pictures classification, which is in the field of computer vision. So we have houses, pictures of houses. We have pictures of something or things that are not houses, and we have a test picture. So we want to train our model to on this and this with the label yes, they are houses. That means y equals 1. And here with the label that these are not houses, that means y equals 0. So we have a logistic regression problem. So, but this is like in computer vision. So how we make a model that actually can learn, can know about this problem. So yeah. So let's see an example in the in the training data set, which is just one picture of the training data set. How do we feed this as an input to our model? Simply, we just like take each pixel. For example, this green rectangle here is kind of a bunch of pixels. So we take the value in each pixel and feed it. But imagine if like this is just imagine this is, I think this is like few pixels. Of course, these numbers are just I just like put them there to show you the example. They are not real. So, but you can see here, this is like really small area of the picture, and you see like this is like really small, and it's already like kind of big input for the model. So you can see that if we feed a whole picture to a model like the traditional machine learning we saw, and we need to feed all this picture like with all its values, it's really huge, like really huge features, because each pixel is considered as one feature. So it is entirely impossible to do that with traditional machine learning. Not entirely, but like super hard. Maybe entirely impossible if the picture is with high resolution, and super hard even for small pictures, like we can see here. So if we use the simple logistic regression we previously saw to classify this picture as a house or not, let's say the image is only 100 by 100 pixels, which is like really small for nowadays pictures. That means 10,000 pixels. If the picture is black and white, so imagine if the picture is black and white, we're gonna have 10,000 pixels. If it's RGB, red, green, blue, that means it's gonna be 30,000 pixels. Imagine 30,000 features, feeding them as an input for a model to train. It's entirely crazy to imagine. So we need definitely another model to learn all these millions of features to feed the data. So yeah, so it's entirely impossible to use traditional machine learning to solve these kind of problems, and we have the solution for that: deep learning, or aka also neural networks. And that's what we're gonna do and see during the course. So yeah, so stay tuned and see you next video.